We saw in the previous topic that statistics can reveal apparent correlations in our data, and we can combine what we know about samples and distributions with some probability to start making hypotheses about the relationships in our data and testing them. Now, hypothesis testing is a cornerstone of data science, and there are many factors to consider. In this course, we're only going to take a quick look at hypothesis testing and get you some basics to get you started. Now, suppose that we have the full population of lemonade sales data, and that the mean number of daily sales is 25 lemonades. Now, let's also suppose that we believe that sales are significantly higher on hot days. Now, one way you might determine this is to take a sample of data for days when the temperature is high and calculate the sample mean. So let's say we take a sample of 30 days with above average temperatures, and the sample mean turns out to be 33. Well, 33 is higher than 25, so we could conclude that we're right, and that sales are significantly higher on hot days. But wait, not so fast. We know that the mean for the sample is higher than the population mean, but is that statistically significant? If I just took a random sample of any 30 days, regardless of temperature, could I reasonably expect to get a sample mean this far above the population mean, just purely by chance? Well, here's the sampling distribution for sales with a sample size of 30. The sampling mean is the same as the population mean, 25. But you can see that it's perfectly possible to take a random sample of 30 observations with a mean as low as 15 or as high as 35. So the real question is, how probable is it that for any random sample of 30, we'd get one with a mean of 33 or higher? And what level of probability am I willing to accept as being within the bounds of simple chance? So to conduct this as a fair test, we set up two hypotheses. The first is called the null hypothesis, and it effectively says that the sample mean for our 30 observations on days with higher than average temperature will not vary significantly from the population mean, allowing for natural random variation in the data. In other words, sales are not significantly higher on hot days. The second hypothesis is called the alternative hypothesis, and in this case it states that the mean sales for hot days is significantly higher than the population mean. Next, we determine a significance level that indicates the probability threshold under which we will reject the null hypothesis in favour of the alternative hypothesis. In other words, how unlikely does our sample mean need to be for us to conclude that the difference in sales is due to more than just random chance? Typically, we indicate the significance level with the Greek letter alpha, and in this case, we'll choose a value of 0.05 or 5%. If we were to draw a curve for our normal sampling distribution, the shaded area under the curve on the right shows the significance level covering the top 5% of the distribution. Now we're ready to conduct our test. Now technically, if we know the standard deviation of the full population, we conduct something called a z-test, but if we don't have that information, and typically we don't, we conduct a t-test. I won't go into the detailed differences between these two tests in this course, but suffice to say that with a big enough sample, a t-test works just as well as a z-test. In Excel, we use the z-test function, which performs the appropriate kind of test depending on whether you supply the standard deviation or not. The z-test function returns something called a p-value, which is actually the probability of observing a sample mean at least as far from the population mean as the one that we got purely by random chance. Now let's suppose that the p-value we get from our test is 0.02, which is smaller than our significance level of 0.05. That means that the probability of observing a mean as extreme as our sample mean by chance is less than the threshold we set. So in this case, we would reject the null hypothesis in favour of the alternative hypothesis. It looks like sales on hot days are significantly higher than average.